Today in this lecture we are going to start a new chapter, integrated optical components. So, the first simple components we will be discussing today, that is actually based on Y-junction, power splitter, combiner and also Mach-Zehnder interferometer. You know, these are the actually some of the important component, passive component I would say, and you can easily understand if you have good knowledge in waveguide theory and coupled mode theory. Coupled mode theory just we have discussed. We will continue that whenever necessary. We will just use those coupled equations and we will be explaining. And today we will be just using a little bit idea of coupled mode theory to understand the working principle of so called Y-junction power splitter, combiner and Mach-Zehnder interferometer. It is one of the most important components among many. Few components are important for integrated optical applications, integrated optical circuits. So, Mach-Zehnder interferometer is one of them. All right. To continue that, first what we will do, we will try to picturize, visualize a 2D waveguide, mathematical model. We want to express a mathematical model for 2D waveguide and in terms of 1D picture. So, I mean to say you can say that, as I mentioned here, it is a 1D mathematical model of 2D waveguide. And then based on that I will try to explain the working principle of Y-junction based on single mode waveguides. And then finally, I will be discussing your Mach-Zehnder interferometer. So, now let us try to discuss first how we can develop a 1D mathematical model, working model of a 2D waveguide. Here one example, as we always consider for a SOI silicon on insulator waveguide, it is a waveguide structure and this is a photonic wire waveguide structure. When this small h, the slab height is 0, then it is called sometimes photonic wire waveguide. And we know that the dominant electric field component for the mth mode, if it is a multi-mode waveguide, number of modes are there. So, mth mode we can just express in this way, Em x y z t. If it is a monochromatic wave, electromagnetic wave propagating along the waveguide axis is along z direction. Then you have a amplitude Am and field distribution, dominant electric field distribution, it may be either in the x direction or y direction. We will be considering that depending on the T like mode or Tm like mode, and then your phase term will be there, omega t minus beta m z, z direction phase will be changing. And we have normalized such that Am square is 1 watt and Em. So, basically we have learned earlier that Em star x y En x y dx, if you integrate you are supposed to get 2 omega mu by beta m delta m n. That is the orthonormality condition. According to that we have derived this expression, that if it is electric field, if m equal to n, so we write this one as 2 omega mu by beta m, and if the mode is normalized to 1 watt, we can say that amplitude square is 1 watt. So, simply all the power unit I can impose on Am square. This is what we learnt before we started the coupled mode theory. Now, we can just see W small h capital H, we can just try to picturize for understanding purpose, explanation purpose. We can just only picturize top view. That means, this is your x axis this is z propagation direction, and then you are looking from the top surface surface region of the waveguide. Then you can see along y direction, along x direction, this is your x here, this is x direction, width is w. So, along x direction we have this is the width. So, from x equal to 0 to w, that is the width. Y is now perpendicular to the screen, and we can have this is the waveguide, it is propagating direction, this one. We can just picturize this, but we should keep in mind that the mode field distributions will be looking like that and they are normalized like that. So, this is some kind of model. Always we won't sketch two dimensional picture or cross sectional view, because we would like to explain, because all these waveguides we will be using for planar circuit, a circuit in a plane. So, in plane whatever changes is happening, that matters. And also we should keep in mind that this device layer thickness is a fixed parameter, that depends on your silicon on insulator wafer you are buying, typically 220 nanometer, and of course, you can leave some small h slab height, and that we are not picturizing here, we are just considering only w, okay, width top view. When I see the top view, that means I am just talking about top pictorial scheme. Fine. Then if I just try to see that okay, there are multiple modes will be there. So, for example, if I write this is the mode field distribution E m x y, this is the mode field distribution of the mth mode. So, that will be actually x y field profile you will be able to see, you can evaluate that, and we have discussed that earlier also when we solved the full vectorial equation for a waveguide modes. However, I know that my height is adjusted such that vertical direction you will be observing in the y direction only one. If you just see this is y direction, because this is h y direction, you will see only one standing mode. Standing that means round trip should be such that one peak will be there, and we can always consider that even though you are increasing your width, if this width is increased, but vertical distribution field distribution profile will not change. Okay. Along h direction, along y direction, field distribution will not change, because as long as capital H is fixed. So, as long as capital H is fixed, we assume that vertical direction field distribution is not changing. So, in this 2D diagram here, along propagation direction from the top, if we just try to see, what we will see that different mode, it will show different type of distribution. Okay. This will be your fundamental mode, that is along whatever I am showing here along x direction. Y direction is always looking like that, whatever I have just shown. So, all the fields y direction will be like this, okay. But along x direction, because width is actually allowing multimode. So, more width you can have more number of modes along that direction, more number of nodes antinodes along x direction, but y direction, since it is a fixed thickness, so we can assume that the field distribution is like this. So, schematically though mathematically we will be writing E naught x y, that means it has a x y distributions. So, what we will be writing, it can be simply written as E naught x and something E naught prime y, y direction here, and E naught here also I can write E 1 x and then E naught prime y. Here I will be saying E 2 x and E naught, that means y direction the field profile same everywhere, E naught prime I am just writing E 3 x y, E naught prime, E 4 x, no not x y, this is x and then E 4 x and then E naught prime y. So, that means if I just normally when we solve, we can just assume that this field distributions are can be actually expressed by separation of variables. So, x dependent variable, y dependent variable is there. Y dependent variable function same everywhere I assumed. Then along x direction I can see the mode distribution will be varying, field distribution will be varying. For fundamental mode will be like almost like a Gaussian, the sinusoidal, then exponential decaying will be there, and then higher order mode x direction you will be getting one plus another minus field at any point, and then higher order modes you will see more number of nodes and antinodes like this. And you must have observed that the evanescent tail as you go for higher order mode, that is extending towards cladding more, that is actually here shown, it is extending more and more. So, if you solve for the higher order modes, then you will see that it will be almost leaky. So, you can have certain number of modes will be supported by this waveguide that you can derive. Okay. This is how we can just show the two dimensional 2D waveguide, but we can just explain in one dimension. One dimension I can sketch what is the field distribution, considering the fact that other direction field distribution does not change for any other modes, all the modes. Okay. Now, that is why we have written we can characterize fundamental mode E naught x and along with its beta naught. Beta naught means we know we have solved earlier omega y c n effective naught, effective index of the fundamental mode. Similarly, I can just represent here this E x beta 1, this one I can represent beta 2, beta 3, beta 4. So, this beta 1, beta 2, beta 3, beta 4 also important besides this field distribution, because they actually decide the phase velocity of the mth mode, because my frequency is same. So, this is your beta m. So, different mode they will have different propagation constant, different effective indices. So, as we know that higher the modes effective index drops, effective index drops means higher mode travels faster, okay. Phase velocity will be higher. So, that is what it is explained. Okay. Now, if we see, but we should keep in mind all the time that this is a 2D waveguide, we are showing in the 2 dimension, and we should keep in mind that this condition valid and amplitude is also valid, that is every mode, all the modes they are normalized to 1 watt. This mode also normalized to 1 watt, this mode also normalized to 1 watt, that means this condition fulfilled for all the modes. That is what we assume for mathematical analysis purpose. Okay. So, if we have 5 watt, that means AM square will be 5, that is it, nothing else, just a scaling factor. So, now instead of field distribution, because I have the power, entire power associated with the mode is symbolized by AM square, and rest of the things are expressed by this, that is the normalization condition. So, probably as far as energy propagation is concerned, power propagation is concerned, we may forget the field distribution, actual field distribution EM x y you may not need to consider all the time. Instead, if I know if there are some coupled mode theory or something in between, some perturbation is there, this AM is going to change, but we always assume that the field distribution is not going to change, okay, that is assumed same. So, that means we do not need to consider for our mathematical model what is the field distribution actually, okay. As long as you can just equivalent all the results, other parameters we can calculate based on that. So, we do not need to see the field distribution. For example, you can see that we have defined kappa. Once we know kappa, kappa is defined something like this. So, E1 star xy, then delta epsilon multiplied by E2 xy and dx dy. So, that is actually kappa you have defined. So, once you define kappa, you do not need to bother about what is the field distribution for further analysis in the coupled mode theory we have seen earlier. So, same way we can always consider that okay, fundamental mode will have amplitude A naught, propagation constant beta naught. A naught actually gives the power it is carrying. Similarly, B naught will give the how fast the phase is moving, phase velocity. We will be, or dispersion relation actually you can come to know from beta naught. And then A1 similarly, that is the power it carries the amplitude of the field, and beta 1 is the propagation constant, and so on all the modes. So, now we can reduce the number of parameters, all the field distributions, omega, t, x, y dependencies, everything we can forget as long as we know what is the field value, amplitude value A naught, beta naught for fundamental mode, A1 beta naught for first order mode, second order, third order, so on. So, this is corresponding to mode index 0, mode index 1, mode index 2 and so on. Mode index we start from 0. Okay. So, this is how we can understand. When we say that fundamental mode, then we can, if we just sketch like this, we can say that this is fundamental mode, its amplitude we can always say okay, it is A naught, and propagation constant whatever I compute from the software or simulation software, then we can write this beta naught, okay, mode solver. Then similarly here amplitude A1 and I can write beta 1 and so on. So, this information is good enough for understanding many of the devices how it works in integrated optics. Okay. So, next, okay, let us move on to a waveguide. Top view it is shown single mode waveguide now. We are just considering single mode waveguide. So, 1D mathematical model of 2D waveguides, it is somewhat we express in terms of A1 and beta, A and beta, amplitude and beta. That is so called I mean for 1D mathematical model for 2D waveguide. So, you are just only considering the propagation direction, how it is changing, phase is changing. Cross sectional direction you do not need to bother about anything as long as you can quantify A naught and beta, that is it for a single mode waveguide. So, we are considering suppose a lossless single mode waveguide, just only one mode support, fundamental mode. So, what I need to consider, field distribution will be like this. I know that I should keep in mind, at least I should not forget the field distribution in the xy direction, only mathematically this part is most important here and beta naught is the important. Of course, frequency is known to you, okay. And if this is the case, if I just consider this is actually say t equal to 0 I am considering, and also I am considering at t equal to 0, z equal to 0 I am considering what is the value, t equal to 0 and z equal to 0 I am just writing A naught. And if here whatever light is coming from this side, if it has some kind of phase phi 1, I just add it. So, this is the phase and amplitude at t equal to 0, z equal to 0. So, this is the z starting point, for example, I can write this one. And then if there is no loss etc. is there after travelling a length of L. So, then what I will be getting, A naught e to the power j phi I is there, along with that it has a propagation constant beta naught. So, that means travelling beta L length. So, it will acquire phase of beta naught L. So, that means I will acquire phase phi I plus beta naught L. So, that means this is also exactly equal to t equal to 0 and z equal to L. So, that means t equal to 0, this is the situation here, t equal to 0, this is the situation at z equal to L. However, if I want to say restrict my discussion only at z equal to 0, then what I can say that this thing will keep on varying as a function of e to the power j omega t, sin omega t, cosine omega t. This value will be as a if I just restrict, if I want to just track what is happening at z equal to 0. So, that means z equal to 0, this value, this is the amplitude, whatever phi value is there you just find as a amplitude, and as a function of time it will be oscillating sinusoidally at the frequency of light, so 200 terahertz around that. Okay. So, similarly here also at z t equal to 0 I consider this thing. Now, if I want to roll over time at this particular point, it will be oscillating with e to the power j omega t. So, that is how it is a travelling wave, it is a phase and time dependent variations, how it will be, that we can express in terms of only amplitude and whatever phase is there, that is good enough, and beta naught. So, we are no more considering the field distributions, whatever the x, y etc. is there, I do not need to consider this thing. Okay. So, this is the lossless case if there is no loss, but you know this type of waveguide you have, for example, if you are making this type of waveguide structure, then you know this is some roughness will be there, this you are fabricating with CMOS industry, some lithography defects will be there, lithography is not always perfect, you cannot get perfect plane in both sides, there will be some roughness will be there. So, there will be some kind of scattering loss you can expect also, and depending on the wavelength and as well as also depending on what you call that some defects in the structure, in the waveguide structure, you can see some kind of scattering losses also, waveguide propagation loss is there. So, in that case how you will represent this one? So, lossy single mode waveguide. So, lossy single mode waveguide, I can say that okay, if this is the case, we already discussed earlier, if there is a loss electromagnetic wave, it will be exponentially decaying. So, e to the power minus alpha x that is actual alpha if it is represented in Nipper per meter in SI unit. Okay. So, that is how you know. Normally if it is amplitude this alpha, we have also already discussed earlier that this so called what do you call that, B's law. So, that I z equal to I naught e to the power alpha naught x, for example, alpha naught x will be 2 alpha, because alpha is amplitude loss coefficient for the amplitude. This is sometimes called loss coefficient for the field amplitude. So, at this point of time, whenever we are representing that field is exponentially decaying because of the loss, this alpha, the dimension should be, this is Nipper per meter. So, accordingly the amplitude will be dropped, along with that you will have this phase, initial phase is there. Always you can set initial phase equal to 0, if phi equal to 0 here, you can put equal to 0 here, then it will be A naught e to the power minus alpha L e to the power j beta naught L, that is it. That would have been the phase. So, you might be wondering why plus sign is there, because you know this travelling wave is e to the power j omega t minus beta L forward direction beta z, but since we are just considering how much phase is there, okay, how much additional phase is acquired here. So, that is why we are writing beta naught L. You can always write minus j also, plus minus, that depends on you. So, as it propagates we are just adding the phase, otherwise here this phase will be, you can write also e to the power minus j beta L, that is also fine. So far so good. Now okay, alpha sometimes you know in the waveguide, in photonic integrated circuit or integrated optical circuits, the waveguide loss normally represent in decibel. So, I tried to just explain here. Suppose if it is Nipper, it is there, whenever you are considering in the amplitude scheme, because normally integrated photonic devices you have to analyze in terms of the amplitudes, because phase is very important, amplitude and phase is very important, because you have to always consider some kind of interference, etc. So, that is why that is important, but sometimes you can see that okay, people are industry or foundry, they are saying that waveguide loss is decibel per centimeter or dB per centimeter, something like that. So, that is actually nothing but the dB definition, you know that anything gain or loss in dB, we say 10 times log of 10 base P output by P input, okay. That is actually decibel power. And if it is voltage, normally that dB, same dB will be written like 20 log of V out by V input. So, V square by R equal to power in terms of circuit point of view. So, here also we can say that loss in dB, I can say that what is the power here and what is the power here. Here power I can write A naught e to the power j phi I times A naught square, A naught star e to the power minus j phi I, right. So, that means complex conjugate you have to take and then you have to multiply, that will be your power. This is A naught square. So, A naught square is nothing but you are considering like a Pi, okay. So, this A naught square is the input power, right, and output power how much it will be? It will be A naught square e to the power minus 2 alpha L, and this one will be complex conjugate, if you take that will be cancelled like j phi 1 to be. So, whenever you are considering power, the phase information is lost basically, okay. So, nevertheless that is what energy point of view we can understand that one. So, I can say that the loss in dB, we can say 10 log of power in the output by taking ratio power in the input, okay. So, A naught square will cancel, okay. So, ultimately this will reduce to this one, loss in dB 10 log 10 e to the power minus 2 alpha L, okay. This alpha you keep in mind, that is actually expressed in Nipper per meter or Nipper per centimeter depending on your L if it is represented in millimeter. So, you can say that Nipper per millimeter, if it is micron, Nipper per micron, then ultimately this alpha L is Nipper, alpha L together it is called Nipper. Okay. So, now if you just move on, loss in dB, this little bit simplification here, what we have. So, this is actually decibel. Okay. This is your normal consideration, exponential thing is there, but what we can do, instead of e to the power minus 2 alpha L, if I can write 10 to the power minus 2 alpha L, we can express, we have to divide it by log a 10, okay, log 10 to the base e. If I divide it, then this instead of exponential power, I can decade power, decimal power I can put 10 to the power this thing. So, if we write that, this is a simple logarithmic relationship. If you do that, what you can get, log of 10 to the base e comes like 2.3026, and here you see base 10 and 10 to the power minus 12. So, log of 10 to the power something x means it is basically x, right. So, that means this x should be multiplied by, okay, multiplied by 10. That means whatever you are getting in the numerator, 20 2 alpha L multiplied by 10, minus sign is there, 20 alpha L by 10. So, if you just simplify, then it will be, you just divide 20 by 2.3 and so on, then you will be getting 8.686 alpha L, minus sign of course, minus sign, that is because of loss, minus sign, because here power is reduced, that loss. So, whenever you are considering loss, you probably you do not need to write minus, you can just simply write plus. Okay. So, in that case, alpha, if you want to represent in terms of decibel per meter SI unit, this L I can remove, okay, then 8.68 multiplied by alpha Nipper meter. So, if you are just L, if you are taking here alpha loss dB in per meter, then I can write that, okay, if Nipper per meter is given, if you just multiply 8.686, then you can get loss in decibel per meter. Okay. So, if alpha instead of Nipper, if it is intensity loss is given, then alpha dB per meter can be written as 4.34, because 2 times this 10 is there and 20 will be coming instead of 2 alpha, that will be only alpha will be coming power relationship. So, that will be 4.343 times alpha, that means intensity loss coefficient. If it is intensity loss coefficient, you multiply it by 4.343, then you will get loss in decibel per meter, and if this alpha is Nipper, then you have to multiply 8.686, then you will be getting loss decibel per meter. That is just a technical thing, sometimes you may need to follow, sometimes people will be talking about loss Nipper per meter and decibel per meter, you should be able to distinguish that. Okay, fine. Now, let us move. Okay. So, we have so far represented this 1D waveguide, 2D waveguide, 1D mathematical model, and also we have represented how amplitude, loss figure and propagation constant is sufficient to understand the wave propagation in a single mode waveguide or multiple mode waveguide. Now, we will be discussing about Y-junction. Okay. So, Y-junction meaning you have to have one input waveguide and it will be split into 2 waveguides, output waveguides, through a Y-junction type structure like this. So, it was very popular long time ago when waveguide cross sections are little bit higher, lithium niobate waveguides and lot of polymer waveguides, people used to design 1:2 power splitter in this form. Okay. Just one waveguide, single mode waveguide, it is this one, and another single mode waveguide, another single mode waveguide, they are identical. This waveguide also identical in the sense, in the, if you see the waveguide dimension, this W value, capital H value and small h value, silicon and insulator waveguide, all these are same. Only thing is that in the xz plane, if it is there, jet propagating waveguide. So, if you are just considering in the surface of the substrate, top view you are looking. So, you can say that in the top view, in the xz plane, propagation direction is changing. Light is propagating, and then if it is propagating here, it should go like this or it should go like this. So, this type of junction you can design such that you can have a very you can have almost no loss in this junction you need to design, because of the junction this type of perturbation will be there, right? So, your waveguide whatever fundamental mode propagating like a orthogonal mode, no power will be dissipated anywhere, it will be carrying, but suddenly it sees some kind of abruption, some kind of perturbation. So, there actually orthogonality condition breaks. So, when orthogonality condition breaks, that means you have to think about the coupled mode theory, that means that particular mode will be disturbed and all other existing mode including radiating modes energy will be, there is a possibility of energy transfer as long as some kind of mode matching happening and phase matching condition happening, two conditions required for coupling. So, this is actually the result of coupled mode theory. You can see that any power you are launching here that may actually get somehow can get lost completely, also very minimal can come here, that type of situation happen. So, you need to design appropriately so that you can minimize your loss to the outside world. Okay. So, what is that? If it is something Y junction like that, you would like to have the single mode waveguide fundamental mode you are showing like this, and this junction suppose something is there, okay, lossless or whatever, then you could see that okay, single mode waveguide here also it will be there, here will be there. So, situation you see the field distribution here, that is actually we are showing in x direction, but ultimately that should be the fundamental mode, that is xy distribution profile, y direction is there, y direction it is not changing for any other modes, it will be also similar type of situation in the y direction probably. Okay, depending on your structure, symmetric, asymmetric cladding or so. So, you can have this thing. So, single mode waveguide you are representing, but you should keep in mind this one, this is a 1D model, mathematical model, and you can always represent with amplitude as I said. Okay. And here also this is same profile, but you see if you carefully see the x coordinate here and x coordinate here is not same. So, you have to appropriately, whenever you are just relating this mode to this mode, you have to appropriately change the coordinate. For example, if this is E naught x y here, then this one will be, I can say that some distribution is there, I can write E x minus d for x greater than d. So, suppose this is the d distance, the center d distance, x minus d and y. Okay. Similarly, here I can write E naught, field distribution will be x plus d, so and then y. So, this type of coordinate will be shifted, only field distribution is same, but they are laterally shifted. So, whenever you are doing some mathematical derivations etc., and you need a field profile distribution also, that time you should keep in mind that the coordinate also should be adjusted appropriately. Okay. Now, you see if this junction is not properly designed, it is abrupt, what can happen? This is scattering, as I mentioned, this is a lumped region where huge perturbation it can happen depending on the angle, how big angle you are creating, and also you see carefully, if you see the width here and width here, it is now different. So, this type of suddenly it says different type of waveguide and it is kind of huge perturbation, a lumped region is there. So, you can expect something will be scattering backward direction, and by outside also it will be scattering, this side will be scattering, and maybe little bit it will go here. Okay. And whatever little bit go into the waveguide, that will take the shape, single mode field distribution, shape will be similar, but only thing is that the power here that will be actually it will be reduced because of the loss acquired here, loss actually because of the scattering losses in the junction, abrupt junction. Okay. Here normally we define some kind of figure of merit. If this Y junction is practically, even though you just theoretically design a good Y splitter, okay, Y junction splitter, but practically you may see some kind of losses also. So, because of the some kind of abruption, it is very difficult to design also good model, good Y junction, but nevertheless whatever value experimentally you get power here P naught, P O 1, P output 1, P output 2, here input power. Okay. We define one figure of merit, excess loss, we call it as a excess loss, sometimes it is represented by EL. Excess loss is you whatever power you are extracting port 1 and port 2, you sum them and take a ratio with the input and take log 10, okay, 10 log 10 of that one. So, this is the total power you are availing at the both output ports, and you are taking ratio of the input ports and take a ratio, that is called excess loss in dB. Okay. And then another thing is that if there are losses, everything is there, it can happen that this type of waveguides, this waveguide and waveguide 1 and waveguide 2, they may not be symmetric. So, their width may be slightly different also, it can happen. Okay. You can design that also. In that case, even though loss is there and something is coupling here, something is coupling here, depending on the waveguide dimension, their angle, maybe this angle is bit bigger, this angle is bit lower. So, in that case, power coupling this waveguide and power coupling this waveguide, they may not be same. So, if that is the case, we can actually find another figure of merit called splitting ratio. Just take a ratio, how much it is splitting. So, if you are getting, say, suppose 2 milliwatt here and here you are getting 1 milliwatt, then splitting ratio is 2. And another thing is that splitter loss. You have waveguide and you have a splitter here. Some losses is there, whatever thing is there. So, I have a splitter, but I am accessing here. So, here I will be obviously I will be seeing less power, and that less power because you have a splitter here. So, because of the splitting here, you will be getting low power here. That is why you are calling that as a splitter loss. Splitter loss P01 divided by P input, that is this. So, if it is something no loss is there and they are symmetric, then here you will be 50% power you will be getting, here 50% power you will be getting. In that case, you will be getting splitter loss, that means about same, that means 50% 50%. So, if you compare with the input, that will be half. P01 by Pi, that will be half exactly. So, in that case, log 210 be half, right. So, you will be getting splitter loss equal to 10 log of 10 half. So, this actually approximately you will be getting 3 dB. So, that is actually called splitter loss. If it is ideal one, that is actually 3 dB. That is why it is sometimes called as a 3 dB power splitter, Y junction power splitter. Okay. So, this thing, now you can do some kind of junction instead of abrupt Y junction. What you could do, you can have a adiabatic, you can have a very small angle, okay, and this thing you can make little bit of smoother instead of random. So, adiabatic and angle is close to 1 degree, 2 degree or something like that. If you make, then it will be going like that and smoothly, slowly. If it is bending is there also, adiabatic you are making here. Okay, smoothly it is changing. That means it is like whatever we have discussed earlier, that during tapered waveguide, right. So, dimensional change, you cannot just interconnect two waveguides, one smaller waveguide width, another bigger waveguide width just directly, because of abrupt junction. You will see lot of losses will be there and all the modes will be excited in the multi-mode waveguide. But if you do slowly you taper single mode waveguide into multi-mode waveguide, then fundamental mode will be excited into the multi-mode waveguide also as a fundamental mode. Otherwise, if it is abrupt, all other modes will be excited. That is sometimes may not be interesting to you, okay, may not be useful for you. So, that is why you can make a slowly tapering out and theta may be small, so that losses here can be minimized. So, you can approximately, you can design some of the device, you can design the theta, particularly lithium niobate waveguide, you can design the loss can be 0.001 dB or something like that. So, you can design that way, assume that there is no loss here. So, in that case, power will be almost 50% going here and almost 50% coming here. So, if you can design such that this junction loss is minimum, then we can call it as a adiabatic. Actually, practically you cannot get complete adiabatic, that means no loss will be at all there, practically it is not possible, but you can actually reduce, minimize the loss here. If you design properly, you can see almost all the power will be coupled to the this one, okay, into the two output ports. Fine. So, again I come back come back to basics, that input waveguide field distribution, if you just represent like AI, E naught, xy, this is the field distribution in the xy dimension. So that you can keep in mind always, you should not forget that field distribution is there. And here output also something amplitude will be A O1, output amplitude 1, output amplitude 2. Output field distribution, since this waveguide and this waveguide they are identical, field distribution I have also used same E naught xy, E naught xy. Field distribution same, only coordinate are different. That has to be introduced whenever you are doing some computation, etc. for other application. But this moment these are just, you have to keep in mind that they are identical waveguide and same propagation constant here, same propagation constant along z direction. Only thing is that here you will be getting A output 1 and A output 2. Only difference here, you do not need to bother about beta naught, because beta naught here and beta naught here all are same, identical waveguide. Propagation constant same, field distribution is also same. So, amplitude is the only difference you can make out here. Okay. That is the reason what we can do, we can just simply say that amplitude A naught 1 and A naught 2 equal to A naught. So, this one, if it is symmetric one, also we can again another constant we can get, actually that is help that will help your problem easier, that amplitude A naught 1, A output 1, A output 2, they should be identical, because waveguides are identical and they are symmetric, this angle they are symmetric and they are identical. So, in that case this one will be this one. So, that is what we have written. And again we know what happens if it is adiabatic, we know that the amplitude, normally if I have E naught xy, that should be AI, that should be equal to AM M EM xy. That is what we have discussed earlier. If it is waveguide coming into a perturbed region in the multimode junctions or something like that, if there are many modes are there, then we can actually say that superposition of all these modes should be equal to the input mode field distribution. So, here you have two field distribution will be there, one mode here, one mode here, right. So, superposition of these two modes should give you the input field distribution, and in that case we know that this AM square, that should be equal to 1 watt. If A1 AI square equal to 1 watt, then all this together will be giving you 1 watt, or you can write that if there are two modes are there, that is why we have written AI square, that is the power associated with the input field, input mode, and this is the power associated with the output 1, and this is the power associated with the output 2. So, these two if you add, because there is no loss at all, adiabatic lossless Y junction, then in that case we can write A naught 1 square equal to plus this one, and this is also A naught square, this is also A naught square, that is what we our assumption, symmetric waveguide. Then we can write AI square equal to 2 A naught square, that is what it is written here. So, if this is the case, then what I can write, A naught should be equal to AI by root 2. So, that means amplitude division when it is happening in the Y junction, if it is AI at the input, here you supposed to get AI by root 2, here you will be getting AI by root 2, that ensures your energy conservation, assuming no loss is there. This is possible to design, okay. Loss up almost like a waveguide loss type of situation it will be created. So, you can assume that thing, okay. Now, you see I have now written AI, AO1, AO2, that means output amplitude 1, output amplitude 2. That is what I forgot everything about xy dependent profile. Only thing is that I know that they are identical waveguides. Since they are identical waveguides, so I am not also considering what is the beta involved also. So, anytime needed, I know that okay, beta value is known to me, I can take that help for further calculation, okay. So, according to our concept, this thing we derived. So, amplitude will be here, here will be this amplitude, straightforward. So, you see it is do not actually mistake it that if this is the amplitude, here amplitude will be A by 2. Sometimes you do mistake that way, because if you do A by 2, just simply amplitude division is there, you may end up with a problem with the fundamental law of physics, because you see what is the energy here, it will be ai square by 4 power, and here if it is ai 2 here also amplitude division, it will be ai square by 4. If you add them, you will be getting ai square by 2, you will be getting just pi square by 2, and you are considering this is lossless. So, if it is lossless and you are only getting half of the power launched at the input waveguide, so that is not correct. So, if you are considering this is a lossless model, lossless Y junction, then amplitude when it is divided, that should be transfer function will be 1 by root 2. Okay, fine. Now, so now if you consider that in the input, if you have a phase like this, some phase initial phase is there phi I, so I can write this one. Now, when it is coming after splitting, I know that amplitude will be this one, amplitude will be this one. Now, because of the splitting, I can say that that particular region, because of the junction, you may get some kind of junction phase phi j and phi j. Since both the waveguides are identical, this phi j and phi j will be same. If they are not identical, little bit different, asymmetric or something like that, this phi j would have been different. So, I need two things, amplitude and phase, for integrated photonic circuit simulation or modeling, right. So, I have used amplitude and phase. Profile I am not considering, as long as I understand they are identical waveguide, and here this one. Now, as it propagates here, it travels some length, right. Okay. Suppose overall length it is traveling, overall length is traveling, that is why whatever phase here it will be acquired by this upper arm, that will be additional phase phi L, and if it is symmetric again additional phase phi L. So, that means whatever phase is there, if everything identical, symmetric, everything is there. So, phase also if you just compare, they are also identical. So, that phase also for some understanding purpose we can also forget. Sometimes people say that okay, if it is amplitude this one and amplitude here will be ai by root 2. And then if you ask what about phase, obviously phase will be there, but here in this case normally phase will be identical. Afterwards if you process them, any interference or everything, if you see they are in phase basically. So, that is why that phase is not so important if it is this type of Y junction power splitter you are considering. Okay. Now, if you are considering, suppose you have a one arm, you have a pi phase shift is there. Okay. Pi phase shift means this field is coming, pi phase shift means I am adding additional pi phase shift. To represent that, I just reverse the field. You see field here positive direction, the field strength I am considering E field positive this direction, E field negative this direction, because pi phase shift it is just reversed, it is shown, amplitude will be negative here. Pi phase shift means amplitude will be negative, the e to the power j pi, e to the power j pi means it is cos pi plus j sin pi. Okay, sin pi equal to 0, cos pi equal to minus 1. Okay. So, that pi phase shift means it will add minus sign to your amplitude. So, in that case what will be there? So, in that case you will be getting okay, whatever phi L will be there, in addition to that minus sign I have added here, minus sign and other things are same. So, in that case also you can consider simply that in phase situation, when there is no phase shift you are adding here, phase shift you can add by external influence, or you can little bit change by waveguide width, dimension, anyway whatever way you can introduce some phase. You can suppose it was a propagation constant beta naught, locally you just change the width little bit, so that you get additional pi phase shift. Because of the additional refractive index change, you can get total phase will be 2 pi by lambda, and say delta n effective changed for a length of L. So, this will be your additional delta phi. So, this delta n effective for that length, this is the length, if this is the length, some maybe 1 micron 2 micron you can consider, and delta n effective because of the width some additional effective index will be changed. If you multiply, that will be, if it is, that is pi, that was I was discussing. If no phase is there, just I simply consider they are in phase. Okay. Now we will be discussing that Y junction, we have, it is not complete yet Y junction. To understand little more about Y junction, I just take help of Mach-Zehnder interferometer. It is a very good device, important device, as I mentioned again and again. It is used for many applications, including a high speed modulator, lithium niobate modulator and silicon modulator. We use this type of structure, Mach-Zehnder interferometer. What it is? If you see from the top, basically identical waveguide, you have a input waveguide, you have a Y junction splitting them, and coming here, and then another Y junction there to combine into another one waveguide. Now, if you see, I am launching here, this is 1 by 1 Mach-Zehnder interferometer, one input, this is input and one output, this side, this is your output. So, 1 by 1 Mach-Zehnder interferometer. And if you are launching here a light with amplitude AI, it may not be normalized. Suppose it was normalized, then AI square would be equal to 1 watt. But if it was not normalized, suppose it can happen that AI square equal to 0.5, that means 500 milliwatt launched, and if it is this one, then 50 milliwatt is launched. So, depending on that, AI is there, that value is known to you, for example AI. Now, we consider Y junction is lossless. So, lossless junction means you know amplitude √2, and they will propagate, they will be propagating with same phase. So, to represent same phase, I have just shown electric field both cases in the same direction, but you know as they propagate they will keep on oscillating, but I want to see what is the relative change is happening or not. Overall whatever change is happening, that is fine. So, relatively if this mode is looking like this mode will be looking like that, because they are travelled same path. At any instant, if this mode is looking like this mode will be looking like this, the field strength will be that particular instant, you will be looking like that. Now, they are combined here. Now, my question is, what would be the A0 amplitude here, this mode, something will be there. I think obviously, if you just see they are lossless, you can say that A0 will be exactly equal to AI, is not it? Nothing will be, because AI is the AI square is the Pi, and A0 square is the P0 square, sorry P0. So, if these are lossless, this is lossless, this is lossless, whatever power you are launching here, everything will be appearing here. So, normally A0, if it is asked, it should be AI, obviously it should be so, right. That is what A0 square equal to AI square, that means P output should be equal to P input, that is true. Now, you see what that mean. If A equal to AI, but here you are getting this one AI √2 and AI √2. If you just simply add them, AI √2, then you would get something like this, sorry 1 by √2, 2 by √2 AI. That means what you would get, √2 AI. √2 AI means power would be 4 AI square. If you just simply add, then power will be 4 times Pi. Where from that power will come? Energy conservation fails. So, if it has to be like this, then what you can do, that whatever this is coming into here, that will be 1 over √2, again √2 fraction. So, from here to here when it is going, transfer function is 1 by √2, and here to here again coming, that is also 1 by √2, here to here is also coming 1 by √2. So, 1 by √2 here and 1 by √2 times will be added there. Then if you add them, then this will be 1 by √2 AI by √2, that means AI by 2 plus AI by 2, that should be equal to AI. So, if it is a lossless case, so any junction from here to here, it is a 1 by √2, again from here to here also A by √2. So, reverse way also A by √2, that is actually thing happening, this is also A by √2. So, now you think more interesting thing, this is a Mach-Zehnder interferometer. Now, what happens, you have power you are launching, amplitude shown A by √2 here, A by √2 here, it propagates identical path, identical things, and suddenly in the path, for example, you block one. That means I want to stop, it will absorb, it will not reach, it will not come out here. Then you have only this one. Then what is happening? If you launch here, coming here, then after here when it is reaching, what would be A0? Because nothing is coming from this side. A0 will be 1 by √2 AI by √2, AI by √2 times, because transfer function is again 1 by √2, 1 by √2, 1 by √2 AI by 2. Then what is the power? Output power AI square by 4, right? AI square by 4, this is output power. that means pi square by 4. In principle here what is the power? Here power was the just p naught by pi by 2, but when it is coming back here power is pi by 4. What is the reason? That means something is being lost here, and again we say that this is lossless Y junction, but you have coming here and when it is adding here you see power is halved. So, that means losses in lossless Y junction, that is what I meant. You have losses in lossless junction. So, something happening, something appearing, that means some power is 50% power is lost here somehow. So, this is paradox. You see, if you just remove this one, then you would get everything here, and when you are stopping here, you are not getting all the power in the output. Whatever power you are supposed to get, 50% is lost. To get that 50% lost one, you need help of this power, this field. That is the beauty, that is the beauty of integrated optics. Here actually interference is happening in the waveguide. I will just explain that quickly. Okay. Same thing it happens. So, whenever it is blocked here, this is coming, this A naught also, it will be like this, not equal to p by 2, say same situation, both the arm it is same situation just shown. Now, let us see, I repeat again that nothing is blocked, both the arms. So, in principle if it is coming, so all the energy conservation point of view I do not have any paradox, everything fine, right. Now, you see, suppose you are giving a pi phase shift here, one arm you are introducing pi phase shift. I discussed that earlier when another junction was not there that time. Pi phase shift is there, with respect to this one I have just shown the field is flipped here, field distribution, and when it is propagating everywhere relatively if I see that is flipped and this is coming like that. Now, this flipped means I can just say that pi phase shift means minus sign will be introduced. So, again you see you just add them together, simply if you add that is also 0, even 1 by root 2 if it is coming here, 1 by root 2 ai by root 2 coming from there, and 1 by root 2 ai by root 2 coming from here, if you add them they are 0, that means power will be 0. So, they are also happening. So, if you block there also something happening, or pi phase shift you are giving, that also happening, that power is completely missing here, ai will be 0, p naught will be 0 here. So, beauty is that if you block one place you are getting 50% power lost, whatever coming from one arm 50% of that is lost in the Y junction, and whenever you are introducing a phase pi in one of the arm, then everything is lost, no power is reaching here, p naught is according to this principle it is lost. Where does light go then? Question. So, that is important, interesting. If you see whenever pi phase shift comes, when it is coming, if you just merge them together slowly this mode and this mode will be, it is adiabatic and they will try to come slowly, and in this region if you say the waveguide width is little bit more. So, in this region it is happened that the higher order mode beta equal to beta 1 that may be existing and that solution is existing. So, this mode will be feeding to the first order mode also, this mode also will be feeding to the first order mode, because they are phase matched here. It will be, if you just merge specially, it will be looking like a E1 xy. It was coming as a E0 xy from this side, and here also E0 xy this side, but this E0 xy is minus phase shift it is there. So, when their distribution it is there, it will be looking like a higher order, it will be exciting to the first order mode. So, when first order mode is excited here, so when pi phase shift is there, pi phase shift is there, so fundamental mode is now converted together, converted into first excitation mode. But that mode again you have a single mode waveguide that cannot be supported, because a higher order mode will not be supported, this is a single mode waveguide. So, that will be lost. So, that is the reason when pi phase shift is there, then power will be lost. So, this is how one can actually, if you actively tune this phase pi 0, pi 0, pi 0, then here light will be on off. So, you can make a switch, you can make a modulator, digital signal, digital optical signal you can get, high light, low light, high light, low light. You can just, if you just somehow externally electronically if you can control this phase, that means you are getting a electro-optic modulator. If this is a data coming, that according to the data you can just modulate your phase and you can get your optical data output, input output. So, this is the principle of electro-optic modulator. Electro-optic modulator is used, we have discussed again and again, for power conversion, electrical to optical conversion, data conversion. Electrical data will be converted into optical data. So, E to O conversion takes place. So, that is how it is used. Okay. So, for that purpose we need to know, we need to find out exact transfer function of this structure. Let us try to see what is the transfer function. Let us say that this phase is phi, not pi, just arbitrary phi. Then what happens? Amplitude comes here, root 2 phi, then e to the power j phi, amplitude comes here, no phase change, coming like that. Then what would be the A naught? A naught will be, you have to multiply 1 by root 2 here, 1 by root 2 here, and then you have to add them. That is what we have done. If you add them together, then what you are getting? This one. Now, this is nothing but A naught equal to 1 by 2 A I by 2 1 e to the power j phi, that is actually A naught, right. Here amplitude will be this one, that phi dependent amplitude will be there. Now, if I want to see power, what is the power here? That means I have to say P naught, P output will be, that means A output and A output star complex conjugate. This is a complex now. This complex conjugate if you multiply, then you are getting this one, A I by 2 1 plus e to the power j phi, A I star, that complex conjugate. A I can be complex also, maybe there is a initial phase is there, we can represent that in terms of phase etc., complex form. So, A I star we are writing by 2 and 1 plus e to the power j phi e to the minus j phi, that is the star. Okay. If you simplify that one, just multiply, then you will be getting P naught will be equal to AI star, that will be there, that can be written as Pi, input power. So, input power phi. So, that means as a function of phi you can actually output power you can modulate. So, if this is some kind of phase modulation is coming, so output power you can also intensity, phase modulation to intensity modulation is conversion taking place. So, if you do this one, this will be square, okay, because this can be written as cos square phi by 2 minus sin square phi by 2 and then 1 is there, okay. Cos phi can be written like this, Pi by 2, then 1 minus sin square phi equal to 2 cos square phi by 2, 2 cos square phi by 2, this 2 will be cancelled, Pi cos square phi by 2. So, that means just simply to relate transfer function. So, that means if I try to find out P naught by Pi, that is the power transfer function, is nothing but cos square phi by 2. So, if phi equal to pi, it is pi by 2 cos pi by 2 0. So, P output will be 0. If pi equal to 0, then P naught will be equal to Pi, and phi equal to intermediate any value, it will be changing like a cosine function. So, it is a lossless Y junction cascaded oppositely, then you can get a Mach-Zehnder interferometer that can be converted into modulator. So, this is very important device architecture. So, whenever you sometimes for large scale integration you may be interested to know the represent the transfer function in a matrix form. You can just represent the transfer function in this Y junction. What is the transfer function you can write? This type of transfer function. If you see that 1 over root 2 1 1 and your input is this one, and this one may be your A1 and A2 for example. So, I can write A1 A2, I can write like this matrix form. A1 will be 1 by root 2 AI, A2 will be 1 by root 2 AI. So, this A2 will be there. So, this can be a transfer matrix for this Y junction. So, it is a just column matrix, 1 by root 2 will be there. And if you have a phi, then we can write this type of transfer matrix. How it is coming? E to the power j phi 0 0 1. Suppose this is your coming as a A1 A2 A3 A4. If you want to get A3 A4, sorry, you want to get A3 A4 you want to get, and then A1 A1, A2. So, whatever A1 you are getting, A3 will be A1 e to the power j phi, if you just do that, and A4 will be A2. Okay. Whatever A2 is there, that will be your A4, and whatever A1 is there, that will be your A3 and e to the power j phi. We have written e to the power j phi. Okay. Now, this that means this matrix you can use as a transfer matrix for this to this. So, first Y junction one transfer matrix, and then second one, because of this phase shifter you can represent a phase shifter transfer function is this one, and then another Y junction, instead of row matrix it will be just column matrix, because you are adding these two. So, that means you can get A naught should be equal to 1 by root 2 1 1, and you can write A by root 2 A by root 2. So, that is what A naught you will be getting, that time A I you will be getting. So, you can actually represent a Mach-Zehnder interferometer in terms of matrix also. So, this matrix ultimately whenever you will be using large scale for example, quantum photonic circuits, as well as you want to have some kind of programmable photonic integrated circuits, that time this transfer matrix will be very, very important, we will be using. And so, I consider here in this lecture, and I can conclude for today's lecture, and following lecture we can discuss about the other important components. So, this is the first thing, Y junction, Mach-Zehnder interferometer we have discussed, and next thing we will be trying to discuss about the coupled equation. Two coupled waveguide can also act as a power splitter, and you can use also two coupled waveguides into 2 by 2 matrix form, 2 by 2 device, and that can be also another type of Mach-Zehnder interferometer. I will be discussing that in the following lecture. Thank you very much.